So just we should know what every component is doing to be able to perform calculation for the size. Okay? Let us read together the given to know what are the inputs. So first, in a refrigerator, we are using R134A as working fluid. So this is the refrigerant. This is a refrigerant type, and this refrigerant is present in your tables. Hala, we'll see it together. We have tables for it. It's like the tables of water, same concept. The mass flow rate through each component is given to be zero point 0.1 kilogram per second. And the power input to the compressor is 5 kilowatt. The following state data are known using the state notation. So first, for the point 1 is the entry point to the compressor. For point 1, we know two characteristics. We know the value of pressure and we know the temperature. Okay, so from here you can go to tables to get other properties that you want. So if you are interested in H, for example, in H1, in S1, you can get these properties from the tables, and we will look at them together. Okay, also for point 2 we also know the properties. We know P2 and T2. So also at point 2, I can determine completely H2 and S2. Okay. Now, for point 3, I know that the quality is 0. This means I am in a saturated liquid point. Okay. And I know the corresponding temperature. So I can find also in the saturated table what is the corresponding value of H and of S if of interest. And at point 4, I just know the temperature. But I want to determine in this problem, first, is the quality at the evaporator inlet. So from this question, I can know that at the evaporator inlet, I should be in the saturated state. Because whenever they ask about quality, so I am in the saturated state. Okay. And then I should find the rate of heat transfer to the evaporator and the rate of heat transfer from the compressor. Okay. Now, how to start? Always try to look at your figure to see. I am interested first in the evaporator, and the quality at evaporator inlet. So my evaporator is here. Inlet of evaporator is just this point. Okay, point 4. So I need to determine what are the conditions at point 4. Okay. Now, to get the conditions at point 4, I should move backward because I know 1 and 2 properties, but I don't know completely states 3 and 4. Okay. So to start with, I will say that I know the temperature here, and I know the temperature at point 3. Okay. But for 3, let me check if I know everything for 3. Okay, look, for 3, I have 2 properties, so it's fine. Since I know the temperature and I know the quality, I know that I am in a saturated liquid state. So point 3 is completely defined. Okay, so from point 3, I can deduce the properties of point 4. Because if I look at my figure, from 3 to 4, I am going through the expansion valve. Okay, and I know that for the expansion valve, I have that S at H at 3 is equal to H at 4. So this is the property of when I have an expansion valve, I have conservation of enthalpy because I don't have heat losses, I don't have work, I have exchange of if you want phases. Yani I was before I had a liquid, and after 4 I have a combination of liquid and vapor. So I have a change in phase. So if you remember when we explained the psychometric chart, in the psychometric chart, we have seen that we can have whenever we go in constant enthalpy, okay, we can change phase. So you can transfer latent heat to sensible heat or the opposite. Okay, so here when you go from warm liquid to liquid plus vapor, okay, then you have converted a part of your heat from sensible to latent. Okay, because you are increasing the percentage of vapor in your system. So what we will do now, okay, what we will do is that we will use the properties of point 3 to get H3, okay? And once I get H3, I can deduce the value of H4. So for point 4, I already know only the temperature. Once I get H4 and I know T4, I can then completely define point 4 and get whatever I want from point 4, okay? Okay. So now they want the quality at 4. So to get X at 4, I should find H4, then calculate, then from H4 and T4, I can get the value of X4. Okay, so this is my strategy for the first question. Okay, so let us go back to the given. I will start, as we said, I will start by state 3. I have a temperature of 30 degrees, a quality of 0, and my refrigerant is R134A. So let us go together to the tables of this refrigerant. So what I advise you to do is to put on a table, on a small paper, to write table B1.3 is for this. In this way, you will find easily the tables, okay? And you put for each page what do you have, so you don't have to search each time. Okay, so here we started with refrigerant. You have several refrigerant for 10A, and you have here what we want. This is what we want, 134A. Okay, we will look in first in the saturated liquid because we have X equals 0, so we have saturated liquid case. And what was the second input? The second input was the temperature, 30 degrees. So I will look at 30 degrees temperature, which is here. Okay, so this is, let me check that this is the table for H. No, this is, so I want the second table. So this is the table for H. Okay, I want HF because I am in the saturated liquid state. So I take the third, if you want here, it's the first column after pressure, just after pressure. Okay, so here for 30 degrees, this is my enthalpy HF. Okay, so H3 is 241.79 kilojoule per kilogram. Then I can say that H3 equal to H4. Okay, so now I know that H4 is 241.79. Then I will say that in the turbine I am always in the saturated zone. Okay, but let me check what is the temperature. The temperature after in point 4 is minus 25 degrees. Okay, minus 25 degrees. So what I should do is I should go to this. I am in the same table, but with a temperature of minus 24, minus 25, sorry. So I go now to the table, and then I read the value that minus 25, it's here. Okay, minus 25, then H will be between these two values here. And it's right, the value of H is 200 something. It's between HF and HG. So to get the quality, all I have to do is to write the equation of quality. I write H4, which is the value I got now, equals to HF, which is 167.38, plus X times HFG, which is 215.57, and I get the value of X. In this way, I can get the quality at the exit of the turbine. Okay. So going back, not sorry, at the exit of the expansion valve. Here, no turbines, guys. Okay. The difference between the cycle for production of electricity will use turbine, but in general the HVAC system we put instead of the turbines an expansion valve, because here we don't want to produce work. It's not our purpose. The expansion valve will will not produce work, and this is what we want, because we don't want to lose energy in work. We want to convert our energy to heat energy. Okay, so here from this information we can get the quality at the evaporator end. So let us check together the method. So as we said, the first step we get H4 241.8, and then we apply H3 equal to H4. Then we get H4 is HF plus X HFG as we did. We get the quality. Okay, so this is the quality at the inlet of evaporator. Next question. The rate of heat transfer to the evaporator. So when they ask about the rate of heat transfer, you should multiply m dot, which is the mass flow rate. Here the mass flow rate is given to be 0.1 kilogram per second. You should multiply m dot by small q. So now your purpose is to find small q. To find small q, you write the energy equation for the evaporator. And in your energy equation, you will need to know the conditions at inlet of the evaporator and the conditions at exit of the evaporator. Okay, so let us check together. We have found now the point properties of point 3. Oh, sorry. Okay, so here, going back to the figure here. Now we are dealing with the evaporator. Okay, the inlet of the evaporator is 0.4. The exit of the evaporator is 0.1. For 0.4, we have just calculated H4. We know it. So now we need to calculate H at 0.1. Okay, to calculate H at 0.1, let us check if we know the properties at 0.1. One is the inlet of the compressor. Yes, at the inlet of compressor, we know everything. It's 100 kilopascal and a temperature of minus 20 degrees. Okay, so now we can go to the table to know in which state we are. So 100 kilopascal and 20 degrees. So let us check. Okay, we have minus 20 degrees is here. A temperature of minus 20 degrees correspond to its saturated pressure is nearly 133. Okay, 133.
Is it saturated or superheated?
No, here, if you want, if you are comparing for the same temperature, okay. If I have a temperature, okay, if I have the pressure that I have higher than the saturated pressure, it will be compressed liquid. But if the pressure is lower than the saturated pressure, my state will be what? It will be superheated. Okay. So here, if you want, since my pressure is 100 kilopascal, which is smaller than 133, then I can say that at the inlet of my compressor, I have a superheated state. Okay. If you go now, if you want to know what is the value of H, you should go to superheated tables and say that my pressure is 100 kilopascal and try to find for minus 20 what will be H. So let us do it together. So here 100 kilopascal is here. Okay, look, 100 kilopascal minus 20, I can just find it here, and you can verify because the saturated temperature at 100 kilopascal is minus 26.54. Since I am above this temperature, then I am in the superheated state, and the value of H at this point, H1, is 387.22. Okay, so now I got the value of H at 1, and I know the value of H at 4, so I can find, if you want, in this way, I can calculate Q in the evaporator. Okay, so going back to the problem. Okay, I have just here. Yes, I have calculated the value of H1. Now I apply for Q dot evaporator. It's M dot H1 minus H4. I replace H1 and H4 by their values. I get Q dot evaporator. And finally, for the compressor, I want to, the final question is to calculate the rate of heat transfer from the compressor. So look, here it is, they told you that we have a heat transfer from the compressor. Okay, so we cannot treat it anymore as isolated compressor. We have a rate of heat transfer. They told me this, and they gave me also the work. The work power input to the compressor is given. So now I will apply the energy equation for the compressor. For the compressor, I need to know the inlet and outlet enthalpy. So here, for the compressor state, I need state 1 and state 2. So already state 1 is calculated. For state 2, I go back to the given. What I know about state 2 is the pressure and the temperature. Okay, so I will check the value of H2 then from the tables. Okay, in general, you can estimate from your look. This is in general, this is a graph, a possible graph for your cycle. Okay, but you have some cycles. Point one can be just here or can be in the superheated region. We have seen together now in this problem that we had point one in the superheated region. It was close to the saturated vapor, but it was little bit far because it's saturated vapor. So superheated, sorry, vapor. So in this case, in this problem, one is not here. Sometimes you can have compressors with point one inside your bell, but in general, we don't recommend for a compressor to have liquid state. This is why we try to move point one towards this point if possible, or even to have it little bit superheated. And of course, point two is always in superheated region. Okay, so because at the end, when you exit your compressor, you have vapor state. Okay, so in general, you can directly know from this graph that two will be in superheated region. So you can directly go and search in superheated region for your state. You know that the pressure at the end of at the exit of the compressor is 800 kilopascal and the temperature is 50 degrees. So you go to the superheated tables and you look at 800 kilopascal. So I will go down now, 800. This is 800 kilopascal and a temperature of 50 degrees. I will read a value for H of 435.11. So all I have to do now is to replace back in the energy equation. I just should pay attention here because they told me that there is a heat transfer for the compressor. I will not put it as 0. So from the energy equation, by applying it to the compressor, I get that the rate of heat is, and I expect it will be negative because I will have loss of heat. So Q should be negative. If you get positive result, there is something wrong. Okay, so is the heat lost by the compressor is equal to m dot h2 minus h1 plus w dot compressor. And please pay attention for always in the energy equation we are using in this material, you have convention for omega dot negative if provided to the system. Since for the compressor you provide work, so you should put -5, and you replace your enthalpies h2 and h1 by their values, and multiplying by m dot, you can get now the value of heat lost by your compressor. So you are losing nearly 0.25 kilo, 21 kilowatt. Okay. Any question on this problem? Okay. So I will ask you to try to do the remaining problems and we will continue the correction. Or if you want, just let us do one more problem. Okay. And once this session will close, we continue the two other problems. We still have two other problems. We continue them next. Okay. So because this is simple, we can do it now. Comparison with Carnot cycle. Let us consider the heat engine shown in the figure that receives a heat transfer rate of 1 megawatt at a high temperature of 550 degrees and reject energy to the ambient surroundings at 300 Kelvin. Work is produced at a rate of 450 kilowatt. We would like to know how much energy is discarded to the ambient surroundings and the engine efficiency, and compare both of these to a Carnot heat engine operating between the same two results. Okay. So here, when we studied heat engines, we have seen that we can never completely transform heat into work. So in any system that is converting heat into work, I will have certain losses. So here, when you provide to a system Q hot, you will expect to get a certain part as work and another part as lost heat. If you can use this lost heat, this is what is called heat recovery, then you can increase the efficiency of your system. Okay? Now, they gave me that Q hot in a system is 1 megawatt. So I am transferring 1 megawatt. So QH, this is equal to 1 megawatt. And from this 1 megawatt, I am just able to extract a work of 450 kilowatt. So if you want to be with the same unit, it's 0.45 megawatt. Okay? Now, since I know the output work and I know the input heat, I know the definition of efficiency is what? Efficiency of a system is the output over the input. Okay, so here my output is the work and my input is the heat. Okay, so it's equal to 0.45 over 1, which is equal to an efficiency of 45%. Okay, in this case, the amount of heat lost will constitute 55% of the initial heat. So if I want to calculate Q dot L, so Q dot L is equal to Q dot H, so the rate of heat provided, minus W dot. Okay, so it's equal to 1 minus 0.45 equals to 0.55 megawatt, which constitute 50% of the initial supplied heat. Okay. Now, if I want to compare this system with Carnot cycle, in the course material, we have derived that the Carnot efficiency is equal to 1 minus the temperature of the low temperature of the second reservoir over the temperature of the hot reservoir. So if you apply it here for the same operating condition, same temperature T hot and same temperature T low, so it's 1 minus the low temperature is we are discharging to the environment, I think, yes, at 300 Kelvin. So please make sure your temperatures are both in Kelvin. So T low is 300, while T high is 550 degrees. Don't forget to convert to Kelvin. So 550 plus 273. This will give you the efficiency of the cycle. Okay, and once you find the efficiency, you can say that the work that can be produced, W dot, that can be produced from a Carnot cycle will be the Carnot efficiency times the amount of heat provided, which is 1 megawatt. So let us check together the numerical values obtained. First, as we did in the first step, I calculated for the system provided what is QL. It is 550 kilowatt, and the efficiency of the system is 45%. Now for the Carnot cycle, by replacing in the equation 1 minus T low over T high, we got an efficiency. Of course, it should be higher. Yani, it's impossible okay, to have an efficiency higher than the Carnot cycle. This is demonstrated theoretically, okay, and experimentally also. So the efficiency of Carnot is 63.5%, which is higher than the efficiency of the system provided as expected. Now, if you want to compare the rates of work and heat rejection, for the Carnot cycle, W dot will be the efficiency of Carnot times Q dot provided, which is 1 megawatt or 1000 kilowatt. So we get W dot for the Carnot cycle will be 635 kilowatt, which is higher, of course, than the provided work in our case, which is 450. And of course, since the work is higher, it's expected that the rejection of heat will be lower. So rejection of heat can be calculated as Q dot H minus W dot. It will be equal to 365 kilowatts, which is lower than 550 kilowatts. Okay, so the actual heat engine has a lower efficiency than the ideal Carnot cycle, with a value of 45%, which is typical for a modern steam power plant. So it's good to know the range of efficiencies of steam power plants, because if you have a problem and you are doing calculation, if you get a value very far from this, then you will know that there is something wrong in the calculation. Okay, so this also implies that the actual engine rejects a larger amount of energy to the ambient surroundings compared with the Carnot heat engine. Okay, any question on this?
But from where we know that the efficiency of the Carnot cycle is 1 minus TL over TH?
Did you watch the videos? It's not covered in the videos you watched until now.
1 minus Q2 over Q1.
Okay. Look, if you maybe you didn't watch, you have several videos, maybe it might be in the next video. بس أكيد حتمرق معكم. I demonstrated this. Okay. And I can demonstrate it now for you if you want. Look, this is the Carnot cycle. I will show it for you here. So in summary, because someone asked me to explain it briefly, so this is Carnot cycle. This is the easiest possible cycle you can face. Carnot cycle is constituted of two isotherms, so two constant temperatures, and two isentropic phases, two constant S. Okay. Now, whenever I have a constant temperature process, if I want to calculate here T1 equals to T2, and here S1 equals to S4, okay, and S2 equals to S3. This is T high. In a Carnot cycle, the upper temperature is called TH, T hot. And the lowest one is called TL. Okay, and what you have is that as you said, the efficiency, okay, is equal to 1 minus Q2 over Q1. Okay, but I want to tell you something. For the calculation of Q is calculated when you have a constant temperature process. Okay, you can calculate Q as T delta S, because Q by definition, okay, Q can be written as integral TdS. Okay, and for constant temperature, if T is constant, then it's equal to T times delta S. Okay, so here you have from 1 to 2. What is the process from 1 to 2? It's an isothermal heat addition in a boiler. So here you will have heat addition in this part, and from 3 to 4 you will have isothermal heat rejection in a condenser. Okay, so you can say that Q1 is the heat gained at the boiler level. So Q1 can be calculated as we said, for constant temperature, it's TH times delta S. Delta S here is S2 minus S1, while Q2 is the heat rejection at constant temperature at the condenser level. So its Q2 here is equal to T low times S2 minus S1. So as your friend said, the definition of efficiency is 1 minus Q2 over Q1. But if you replace Q2 and Q1 by the values we got together, you will see that S2 and S1 are the same. And here, for the second one to be accurate, I should write S3 minus S4. Okay, but since you have isentropic processes between 1 and 4 and between 2 and 3, you can say that S2 is equal to S3. So you can replace S3 by 2 and you can replace S4 by S1. So now if you replace back into your equation, when you do the ratio, S2 minus S1 will simplify, and you will end up with the following result, that the efficiency is equal to 1 minus T low over T high. Okay?
Okay.
Is it clear for the one who asked me about Carnot cycle, or do you want me to give more details? So please, if you have
Yes,
any,
clear, doctor.
okay, if you have please any additional question, ask. Okay, so we are done for today. Okay, we still just have 2 problems. Please do practice, because these problems will seem for you very simple, but if you don't do practice in the exam, you will face problems. So in the exams, many students forget to convert units. Many students, for example, take a lot of time to put the conditions in the problem. Once you do practice, you will do this in a very fast way. So you will save your time in the exam. And time is very important in the exam. Okay, so please do practice. Okay. So we will continue the correction of this problem next time. And if you try to do them, we can you can know what are your difficulties, and you can ask me your questions when we do them together. Okay. And concerning the projects, okay, so I received the majority of your projects. For the one who didn't submit, please hurry up. Okay. And if any group is feeling ready to present, just tell me. Okay. And from now on, once each session we will try to start with presentations. So mainly after the exam, we will do a lot of presentations. But if someone is ready and wants to finish from the project, you can tell me, so that we can do next week or the week after, we can start presentations. Okay. Okay. So see you next time. Bye bye.